My name is Grygleski. I'm a developer advocate at IBM, and specifically, I work for the team. We actually promote like Java-related product offerings, and actually purely technologies too, I'd say, because IBM is much like an open source company versus like the old style. If everybody, when I go to talk at different places, there are still people asking, kind of seems to carry the impression that IBM is a typewriter company, meaning like old, like they're still doing the mainframes. Of course, it's no longer the case. It's like we are very much into open source. For example, my team, my manager is actually OSGI president, and then we also have Eclipse Foundation contributors working on my team and other teams as well, and also the president of Apache Software Foundation. He works on my team as well. We're a team of 12 people. But I'm like one among 4 of us who are doing Java developer advocacy. And I think one of whom my colleagues, Sebastian, was here in October and did a talk too. I think some of you probably have come and saw him talk too. So I work with Sebastian, but I'm based in Chicago. So also too, I'm a community organizer. So I also run the Chicago Java Users Group. So every time if I go to places, chances to talk at Java Users Group, I definitely welcome that, because I myself, I run events, and so I also like, well, for me, I really like meeting folks too, and everywhere I go, I feel like I see you, I feel like it's just my members from my organization. So I again welcome you to come to my talk. And sorry, I think I talked a little too long, but yeah, so my talk, well, actually today we are myself and Oleg too, and I'm sure everybody knows Oleg from Keith. So yeah, and we were supposed to actually do another talk, but that talk too, unfortunately, both of us have been running a bit short of time. So that one we will do it. We promise we'll come back and do it. But today too, it's just we won't do that. But I will be doing my talk, which is Reactive for the Impatient. It's essentially an introduction to reactive programming and reactive systems. So as such, it's a bit of an introductory topic, so it doesn't go very deep, but I'll let Oleg talk a bit more about reactive streams, and that's what he's going to be talking about. So yeah, without further ado, let me start. So I named my topic actually Reactive for the Impatient, because essentially reactive programming, if you think deeper, is essentially designed for impatient people like us. We are all impatient, by nature. We want systems to be highly responsive. Ultimately, that's what we want to do. Highly responsive and very resilient and able to scale. And that's kind of like the core, one of the 3 core tenets of reactive systems. So let me go, yeah. Oops, actually I have to face this, yes. So just a quick thing too. So today, again, it's an introduction, and now popular Java libraries and toolkits, and they are RxJava, Spring Reactor, Akka, and also Eclipse Vertex. Actually, may I see how many of you are already doing some form or maybe very deep reactive programming or reactive systems? Have anybody do? Oh, okay, so it's Andrew. So yeah, of course, yeah. So yeah, and no problem. Seems like everywhere I go now, I travel around the world, it seems to be the case. Most folks are curious about reactive systems, reactive programming, but just have not had a chance yet. Yeah, your organizations have not made the switch yet. And that's very understandable, because it is kind of requires you a different way of thinking. So now I'm hoping that this talk will introduce you to that concept and also get you excited to want to start using it if you haven't already done so. So, okay. So let me then first talk about like why reactive. So reactive as such is not a newest concept in the whole world. And as such, for example, like Akka system that comes out of Lightband, this company that's based in Sweden, they are the founder, inventor of Scala. Professor Martin Odersky actually started Lightband. Maybe some of you have heard of Akka. So they developed Akka systems. So Akka is essentially a reactive systems, and it's very sophisticated and makes use of an actor model itself. Actually, is like a hierarchical system. Like that's how they force you to do things, using the actor model. So that actor model actually came out in 1980s, and that actually came out of during the time when telecommunications was like requiring a lot of real-time kind of capability. So as such too, the actor model is built specifically for highly responsive systems that, if you think about it, telecommunications to have like bidirectional kind of communication. So that's essentially the case, right? And you want to have communications that happens real fast, and they're both, able to communicate on the same channel, being like able to react in real time. So anyway, so why reactive? So why now? So the reason is that in like say within the past 10 years, like all of the hardware has advanced a lot. So as such too, it also basically pushes software to go forward. And essentially too, in the past, when we have single CPU or single core machines, so everything is became take for granted. Your software is written, essentially using like single thread, and that's kind of the scenario. So, but now, like with machines being so capable, like on a hardware level, so you want to have software being able to get caught up and take advantage of this hardware. For example, multi-core machines, you actually have like one processor per core to process your systems, things like that. So it can actually handle this kind of concurrency in a much sophisticated fashion. And then of course there's virtualization and cloud storage, all cloud strategies, all these are pushing like software to go forward in a more sophisticated way. And of course too, ultimately too, is the software itself. We as human beings, we have created this demand too. If you think about it, we used to be, when cell phone first came out, each household maybe share one cell phone. But now, guess what? We not only do we have one cell phone per person, we have multiple devices. You can have multiple things like your cell phone, your laptops, your tablets, and notebooks and whatnot. So that's why too is driving the reactive software systems to kind of go further at this point. So then let's talk about what is reactive. So first of all, I'd like to point this out to you if you haven't already heard about this Reactive Manifesto. Essentially, it provides a guidelines and define what reactive systems should be. So if you visit this link, I won't go into all the details, but I will talk a bit about the basic principle in the next slide. So this is the link, and it's www.reactivemanifesto.org, and I have it towards the end of my slide to this link. So if you look that up, you can then kind of take a look to see what this manifesto is, the specifications is like. But ultimately too, what it's trying to do is promising a very high, the systems needs to be highly responsive and has to be very flexible. And actually, not only is highly flexible and responsive, but it also needs to be very resilient, able to recover from failure in a very timely manner. And also, too, how it handles failure, too, in general, is just more sophisticated. And now, whenever we talk about reactive systems these days, we always touch upon these 4 principles, which is laid out in the Reactive Manifesto. So first and foremost is the systems that are, needs to be very reactive, responsive, meaning that we don't want to have any requests coming out. We don't want to have to wait for a long time. Responses needs to come back in a very timely manner. That's essentially is being responsive. And being able to do that requires systems to be, in general, it's basically you have clustering systems, and you have replication, isolation of different parts of your system. So then you can kind of do, have systems go up and down much more quicker. So that then brings to the next principle, which is elasticity. By elastic, we mean that systems can basically handle the resources can basically increase if there are increased number of requests coming into your systems. You want to have more resources able to process these demands. And then if there's, basically if your system is idle, there aren't that many requests, then you can basically return the resources to some pool. They can service some other system's requests, that type. So by saying that, it means that system has to be really scalable. And overall, your throughput should not suffer, is what elasticity means. And then another property of being very reactive for any systems is resiliency. So by resilient, it means that systems, if it goes down, it shouldn't be down for too long. Basically, it needs to bounce back quite quickly. You also don't want any failure occurs and delay all of the processing. So that's what resiliency means. And that, again, is being achieved by replication of your systems. And for example, in Akka system too, it has Akka clustering, the sharding and everything. It's basically divide up all your data into different storage areas and all that. So then it kind of helps too in terms of resiliency aspect of a system. And then all three of these principles are basically able to kind of uphold their principles is because all reactive systems are essentially message-driven. And in order, basically, message-driven means that the components themselves, how they talk among themselves are through messaging. And I'll talk a little bit too and compare message-driven versus event-driven. Because most, for all reactive programming, we are also talking about event-driven. These are like systems that are being driven by events. Something happens and it triggers some action. That's what it drives the logic forward. But there's a slight difference between event-driven and message-driven, which I'll be talking about in the next slide. But first of all, let me point out some very important distinctions, because I have heard people who are not familiar with Java too, they actually come to my talk thinking that it is React.js, the JavaScript. Now, while JavaScript is, React, it supports some of the principles, right, of reactive systems, very responsive, essentially, all these things, but they are not the same. I'm sure you all know. And so React.js is really JavaScript, and then React.native is for mobile, and that's in TypeScript. So that I want to point out. And then another thing too is that there's reactive programming, and then there's functional reactive programming, and then there's also reactive systems and architecture. So all these, they are not the same. I'm using a picture of fruit because if you look at fruit, and they are fruit. So just want to point that out. So reactive programming too, in a nutshell, essentially what drives the logic forward is basically in reactive programming, you're handling events. So events carry data. So basically it's the change of state of the data. That's what drives your workflow to go forward in a reactive systems or reactive programming environment. Whereas for functional reactive programming, that actually we'll talk a bit more about primitives, about threads. So if there's thread is executing and the thread keeps going, that's what it drives the logic forward. So that's not the same as reactive programming events kind of being driven forward. And then there's also reactive systems and architecture, and for that, it's basically another level up. It's basically bringing asynchronous systems another level. So you're not only dealing with one component. For example, in a large system, you have many components. For example, in microservices kind of environment, you have many microservices. They're essentially independent component, does its own thing. So they need somehow to be able to coordinate with one another. They need to function in a very coherent manner. And let me give you an example. And maybe I saw some of you who came to my talk at DevVox Ukraine, so you might have heard about this. I was actually in India for, there was a conference back in April. So that was my first time I went to India. And if you have been to India, it's actually a very interesting country. I found it so fascinating. But one aspect is so fascinating that I keep telling everybody that I met who haven't been there, is they don't actually have traffic lights. And they don't have, they have traffic lanes going each direction, but there are no traffic lights. And there's no crosswalk. So how do you cross the street? You basically, so first of all, I work with this guy, Pratik, who is actually originally from India. So we went to India together, and my other teammate, Billy, and a bunch of us too. So we have to cross the street, but can you imagine there are cars and buses, and of course there are no traffic light, everybody rushed through the street like crazy. Then we have to cross the street. So in some sense, if you think of it in computing sense, it's sort of like doing reactive in a computing way, right? You're trying to be reactive, reacting to the flow of traffic. So you basically, when you cross the street, okay, there are buses, there are shuttle buses, vans and taxis, and cars and tuk-tuks. So these tuk-tuks are like three-wheelers, essentially, running through the streets. And they go pretty fast, too. They carry people, right? It's a very economical way to get around. And so for us, in order to cross the street, I remember the first time my eyes were like, oh my gosh, we got to cross the street. How are we going to cross? And Pratik, my teammate, my team lead, saying, hey, everybody get ready. So we just wait at the side of the road, look at the direction of traffic coming. Then basically, you look for a gap in the traffic. Then when it's ready, you dash across the street to the median strip in your road. Switch to the other direction of the traffic. Then you do the same thing. You repeat, but just face the other direction. You find a spot in which there's some gap, then you dash across the street. Now, why I'm talking about this is that in some ways it's like reactive systems, right? You need to be very reactive, highly reactive, but you also want to avoid collision. So otherwise, then you probably end up, being in an emergency room. So, or something bad could be worse too. So essentially, I'm just trying to say, in some ways, if you kind of think of reactive systems, you can kind of liken it to this kind of scenario. You have many different systems, many components, like all talking different things, and you try to like make some coherence among all of them to operate in a very coherent manner, so then they don't all kind of jam together. And if you think about it too, there's also back pressure that can build up as well if you hold up the traffic too long, because after all, the cars, they do stop when you're trying to cross the street. They won't try to hit you, but you could also have a scenario in which accident can happen. So, but again, I just want to point that out to you. But again, that's more like dealing with like reactive systems architecture. You're at kind of higher level. You're dealing with the whole system, ecosystem as a whole. Okay, then let me go to talking about event-driven and message-driven. So anytime we talk about reactive programming, reactive systems, we're dealing with system that's asynchronous in nature and has a lot of calls that comes in that don't wait. You just, you make a call, asynchronous. You want to do something, request, and then you submit your request. You then turn around and go do something else. You don't get held back by it. You don't waste your time. You go do something else. And that's more like event-driven. But then there's a difference too between event-driven and message-driven. So by event-driven, we're talking about messages being almost like broadcasts, like pub-sub kind of model. So messages get published, but there's no specific address that's associated with these messages. So it's up to those who are interested in the messages, they subscribe. Maybe like kind of the old Java messaging systems, you do pub-sub, right, and JMS. And so it's more like a pub-sub kind of scenario. Those are event-driven. And so let's say in RxJava or in Spring Reactor, then you actually are doing like subscribe in some ways to that's what you're doing. You have observables, and there are observers that are observing your messages. Those who are interested, they can basically subscribe to and kind of take the message and act accordingly. Whereas in message-driven systems, we're talking about messages that have there are two kind of message sender and recipients. They change role too, but essentially you have like known addresses between these two endpoints. They are talking to each other. So that's like message driven. That has an address associated with their messages. It knows where the message will go to. So that's message driven. So those are the differences. Now, let me kind of move on to this, and you're wondering why do I bring up a bowl of noodles? The reason is that when I first started doing this talk, I was thinking what would be a good example to show the audience if folks haven't done reactive, and thinking of what would be a scenario that we can use reactive systems. Now, there are tons of ways you can be very creative, or tons of use cases. You can use reactive style of programming or reactive systems and all these things. But it's just that this happens to be something was on my mind because I was in Tokyo too for a Java Users Group conference. So it brought to mind. But for now, I won't go into all the details, but just want to get you interested. So then I'm not just like keep talking, something, but just get you interested to see why I'm trying to use a noodle shop case to kind of think of using reactive programming to do the work. But first of all, then I'll talk a bit about reactive programming, so some of the patterns and terminologies. So essentially, too, reactivity, when you hear about it, it means it's the process of responding to external stimuli and propagating events. And then for events, they are really the stimuli. It's basically expecting some action, trigger some action. And then streams are essentially primitive representations of a sequence of data elements, while observables, they are really stream of events in this case. And they are this term is used especially by RxJava, and also I think Pivotal Reactor also use observables too. And the design patterns, the design patterns being used will be like iterator, observer patterns, and composite patterns in reactive programming. Okay, and then here, I just want to point out too, if you haven't already seen this is, I borrow it from the Rx Model website. And basically explaining like doing programming, streams programming. So basically these different color lines in here, they just represent different streams, but like it's the different state of the stream. So the very top one here, streams, is basically an open stream. It's just waiting for some events to happen. So it's just waiting at this state. But the second one in here, you see some different shapes, and then also a perpendicular line like this. And this one actually represents, yes, there are some events and carrying some data. Then what happens is that your stream keeps going. It's like a timeline too, and this one actually has a definitive time to it. So the stream terminates at this point after processing some events. And then the third one here is basically also some shapes, and then you see an X. This X basically stands for an error event. So in reactive programming, in that world, when you do reactive programming, the events themselves are first-class citizens. So they are no different in terms of them, you know, think of it first-class citizen. They are just another event, and as such, they are error events that needs to be handled accordingly. And then there's bottom in here is that there's a stream, but over here is that you see a bunch of marbles, and then there's basically an open-ended stream in here. That's what it represents. So. And here is just an example too. If when we talk about reactive programming, we're talking about you operate on the streams. So basically too, it used to be, you may be, some people actually talk to me and then arguing with saying that, well, it's kind of no different than if you just, the old way of doing asynchronous way is to basically use like event listener, for example, and those are really involves callback. It's actually, strictly speaking, in reactive programming, you still have some callback underneath the hood, kind of, you know, in the lower level. But as such, too, to actually operate on reactive streams, you basically, we call it, what we call is operator. You operate on the streams. And so this is just an example of like reactive programming. You basically use a map operator, and that's pretty common as an operator to operate on the stream. So over here, you see, for example, this, I'm just giving an example here. You have a stream and it carries it has some events, it carries some data, 1, 2, and 3. Then you apply like a map operator to it. In this case, it's just multiply all the elements, each one of them by 10. And then immediately too, then you can do a .subscribe that will basically consume what's being produced. And so you can see too, like using reactive programming is actually make your program more elegant, because if you think of the traditional way of doing things, then you have to first like parse your input and then kind of process it accordingly and do all these things and multiply, and then you then have to basically, in this case, when you do it, basically do a system out print line, for example. But in this case, you can actually have all three, like producer and operator and also the subscriber, all within one statement. So that's like one advantage of like doing reactive style or functional style programming. You can kind of make your code a lot more kind of concise in this case. So in this case, then you see the output. My subscribe in this case is basically take the transform data and print it out to the system output, to the system console. So in this case, you see for 1, 2, and 3 that got passed in, this will become, you see item 10, item 20, and item 30. So again, this is just an example, and if you are interested and would like to investigate and understand more, then you can visit the rxmarbles.com, that site. It actually has many other operators that you can try out like interactively too. For example, like another common one would be like a filter operator. So that will be very useful. For example, in large stream of data coming into your system, you want to quickly basically filter it out, maybe certain attributes, like for example, company data. You can say I want to look for employees who have served at the company before 1950 or something, for example. So then you can do a quick filter to do it, rather than the old traditional way, if this or if that, make the code a lot more, just a lot kind of messier in that case. So. And now, I'll move on to talking about reactive systems design. These are just some of the like large patterns that basically, when we come to dealing with a system of many components, they probably are implemented using reactive programming, kind of style. But as such too, in order to manage all of these components, then we have divided into different ways of programming them. And these are just some of the examples of groups of patterns that you will use. For example, like state management and persistent pattern, like those would be something like domain object, event sourcing, event stream. Those are more like state management and manage the state and persistence of your components. And there's also flow control patterns such as like throttling and pull and drop, for example. And then for message flow patterns, you can have saga pattern, you might have heard too maybe, and forward flow and aggregator, for example. And then there's also, like these actually gets kind of deep too, and there's actually a book that's written about these patterns, which I have it towards the end of my slide, so if you're interested. But here, just wanted to point out, so you can see there are also patterns that handles fault tolerance and recovery patterns, and one of the more popular ones would be like a circuit breaker type of pattern, that basically if error occurs, you want to essentially break it so you don't propagate your error throughout your whole life cycle of your system. And replication patterns, as well as like resource management, all these, they are like just broadly you categorize these patterns to handle your reactive systems. Okay, I think. Okay, so here too, I just wanted to bring out just highlight a couple things about reactive systems. So when we talk about reactive systems today, or how many of you are already doing microservices? Maybe you have some, oh, okay, so a few of you. So yeah, so the idea is that you want to break up your monolith, right? So it's traditional way of doing things. You tend to maybe have one JVM, just everybody is relying on the same container, same environment to do things. So then you can imagine if you try to do any maintenance, it's going to be messy because then you have to bring down the whole system in order to upgrade some small parts of your system. So the idea of microservices, you want to divide things up, and so then you can have each part handle their own thing. So then, in that case too, it makes the maintenance and upgrade a lot more easier in that case. So, and then reactive systems itself too, the nature, by such nature, is actually, it lends itself quite well into doing microservices implementation, because as such, reactive systems, one of the kind of core principle as we talk about will be responsiveness and being like the message-driven capability. We're already talking about systems that are all broken up, they're isolated, so then you don't have two components maybe doing the same thing all live within the same container, for example. So as such, reactive microservices is kind of a very naturally it fits each other very well. And okay, so one of the patterns I also want to point out would be like circuit breakers. So maybe if some of you have done some circuit breaker thing, essentially theory is that it's basically you have error come in, some error events, then you don't want the events to keep being there. So you want to respond to it quickly and handle it and basically essentially break your error from propagating. You handle it so then you don't get it propagate throughout your whole system. And then another very important aspect of having reactive systems today, and also later I'll talk in a few slides talking about reactive streams. That specification is to handle back pressure. Is that you can have many requests coming in, and basically whoever is processing it is not able to handle it in time. So then as a result, all of your requests get all backed up. So then that's back pressure. So basically too, in reactive streams and most of the reactive systems are trying to address is to how do you handle this scenario in which you get too many requests coming in. So one of the things that you can do is that you increase resources to handle your requests, or you can also slow down the input too. Basically some throttling pattern, you can also help to slow it down, for example, right? So it depends on scenario. But also one example too, life example, I remember too, when I was actually, a couple of weeks ago, I was in North Carolina in the US for a conference called All Things Open, and there were 5,000 people. And actually at that conference was interesting, we had after party, and then there was only one bar, and then two bartenders, and 5,000 people line up, and we were all given drink tickets. Can you imagine? I was looking at that line, it was so long, it's one single line, and maybe they split into two somehow. But can you imagine a couple thousand, or maybe not 5,000 people show up, but maybe I'd say close to 900 or 1,000 people on that first night. So you can see that that's a life example of back pressure. You get too many requests lined up, you don't have enough servers, bartenders servicing you. So as a result, I was, myself and a bunch of people too, we were stood in line for almost an hour. But by the time we got up to the bartender, and can you believe he was saying that, sorry guys, we actually cannot serve you anymore because we already have reached our limit of serving the drinks. We're like, what? So anyway, that's just an example of back pressure in real life, right? So in computing terms, we want to have mechanism to handle this kind of scenario. So And another thing too about reactive systems too is to handle like, any kind of data intensive system, you want the data to be highly available. So the high availability and also the consistency of the data. You don't want the data to be like wrong, come back wrong. However, there's this, I highlight in here too, there's this CAP theorem too, if you're familiar with it. It's basically saying that any kind of data intensive systems, you have three aspects to it. The availability of data, the consistency of data, and also the network partition. So network partition, essentially, it's data being connected to some network source. But the theorem basically is stating that any data-intensive systems, you have three aspects of it, but only two can actually coexist at the same time. But network partition is a given, then in that case, one of these aspects of your systems is either availability of data or the consistency of the data will have to relax a little bit. And in general too, we're saying that that's okay, we can suffer a little bit, have the consistency part, because anytime any system, that's live, then you can have many updates going on, updating certain records. And if you query it initially too, the data may not be correct, that's okay, you just want it to be kind of sent back to respond back quicker. Because we're just keep querying it, then eventually, the theory is that eventually the update would slow down, so if you query it, the data itself will become accurate, and that's what it is. So, but that's just want to point out to you, because in any kind of true like reactive systems, for example, like Akka, it actually has a pretty sophisticated way of handling this type of scenario, the eventual consistency aspect of data. Okay, let me see. Oops, I think I'm talking too much. So, okay, now. Then I'll talk about reactive streams, which actually Oleg will be talking a bit more, but here I just want to touch upon, because in the reactive world we have specification that's actually came out just quite recently, like since 2013, so it's within the past 5, 6, or 7 years. So that's reactive streams, and this one is actually a standard for basically for asynchronous stream processing with non-blocking back pressure support. So that's what it is. And currently, too, the working groups that are supporting it will include Netflix, Pivotal, Lightband, and some other companies too, but these are kind of the more major players. And then there's also then a newer standard, Foundation, just also recently came out a month or two ago in September. It's actually called Reactive Foundation, and it comes out of Linux Foundation. Essentially, too, there are 6 companies, and I'll just go to the next slide. And this one I borrowed basically from Spring One platform. They basically announced the Reactive Foundation there. And basically it's supporting a reactive socket is like a latest like binary bidirectional protocol. I guess Oleg can correct me too, because Oleg is very actively involved with that. And these are the companies that are taking part in this foundation. So Facebook, Netify, and Lightband, Alibaba Cloud, and Pivotal, and vLingo. So our socket is essentially an open source library, small interface. I don't think there's implementation. Is that correct? Yeah, there is? Okay, all right, yeah. But Reactive Streams itself, I want to point out, is that it doesn't specify any implementations. Reactive Streams itself is a specification that only specifies the interface, and there are only 4, publish, subscribe, pipeline, and some processor, I'd like to say. So there are few interfaces, but the idea is that each vendor, they will implement things their own way, but they still follow the specification of these 4 interfaces. But again, our socket is an implementation of Reactive Streams. And over here too is supposed to be like really fast, and it is very fast. And so like new capabilities like streaming, resumption, cancellations will ease development. And there's reactive back pressure, flow control, eliminates like complex configuration. And basically, it aims at being agnostic for the transport layer too. So it supports TCP, HTTP, and also, I guess, Aeron too. So, but basically, it aims at being like very flexible as this bidirectional capability too. And it's basically, a sophistication above like the older WebSocket over HTTP way of doing communications. So. Okay, so now I'll move on and then talk about what about like in reactive programming, reactive systems, and what about microservices. So I just like to point out is that, oops, I think I meant to say this. So reactive programming is basically used within a microservice because it's used for implementing service internal logic and some data flow kind of mechanism. Whereas reactive systems are basically used in between microservices, because then, yeah, this is just how things are being kind of defined in this case, because reactive systems are essentially used for bridging all of these different components trying to communicate with one another using like message-driven approach. Okay. And then here, I just want to point out too, because IBM actually has a partnership with Lightband, so with the Akka framework, is that there's a since we talk about microservices, so Lagom is basically an opinionated microservices framework that comes out of Lightband, and it's built on top of Akka cluster and also the Play framework too that comes from Lightband. And it basically has RPC style programming, and it implements the message broker API is basically implemented in Akka Streams and Kafka. And also then the persistence based on like domain-driven design concept, and also it supports like event sourcing and CQRS, which stands for command query responsibility segregation. So these things I just want to point out to you, like keywords. If you're interested, you can look those up too. Okay, so now I'll kind of quickly go into the noodle shop scenario. Why I brought up the noodles shop is because I was thinking, well, maybe, you know, while I was actually on the airplane one time, well, coming back from Tokyo too, was thinking, I said, oh, maybe we can kind of use some noodle shop scenario to implement, like automate a system for you to order noodles, right, from a noodle shop in Japan. But let me kind of go back one. Here, just want to point out, so if you have ever been to Japan, you may notice, or if you haven't, I'll just let you know here, is that when you go into a noodle shop, a typical noodle shop in Tokyo, there are no tables and chairs. So you go in, there's only vending machines. So kind of like semi-automated, well, kind of automated, but the thing is, in computing terms, it's a very slow thing, because you have to be personally to be there and use a physical vending machine. And most of the places only have one vending machine. So can you imagine if a very good noodle shop, you can have like customers build up against, you know, a lot of back pressure. So you only have one machine, and then you punch in and order your food, then you put in your money, and doesn't even take credit card, most of them. Actually, I think all of them don't take credit card for some reason. And then you take a ticket. Then with the ticket, then you give your ticket to the servers at the bar. And you don't have regular tables and chairs, you just sit around a bar. So that's what it is. And so I was thinking, oh, that might be a good use case for using like reactive programming way of doing things. So say we are very busy programmers, we don't want to waste time, and so we want to order food. So how about like do a mobile app, essentially maybe using React Native to do a mobile app, and very responsive kind of style of placing order. So once your orders get placed in, it's kind of, in computing terms, let's say if you use an RxJava framework, RxJS too even, and you can basically, they are like observables, they are events that comes in. So essentially then will be the waitresses that are observers. They are the ones that will consume these events that comes in. They need to do something about it. But using this simplistic case of a noodle shop in Japan, then you can't really tell the cook to start cooking noodles, because you need to make sure that the customer coming in, they can sit down, you know, by the bar area, get a seat. So here I'm thinking, oh, we can actually have a open seat kind of observables, kind of essentially if a seat opens up, then you basically trigger an event to that. So in that case too, then your waiters or waitresses will then have to be basically take two observables, two streams, and basically saying, okay, you have an order coming in, and you also want to make sure there's an open seat available. Then at that point, you can then tell the cook to actually cook your noodles, cook your ramen noodles. And then in that case too, you know, we can also implement something like a notifier system. Once the cook receives the order, then we can actually trigger a notification message to your cell phone when you're busy doing your work. You can actually get a notification and say, oh, your noodles are going to be cooked and ready in 10 minutes, something like that. So in that case, and it's actually, if you think about it in computing terms, it's actually more efficient, because then you don't have to wait, essentially. You can be doing something else. All you need to do is place the order, somebody do your noodles, and when it's almost ready, you get notified. Then you actually go to the noodle shop, and when you get there, actually the seat is available, and then your noodles will come. So essentially, I'm thinking, though this isn't like the most accurate way of describing, but that may be like a use case that you can think of using reactive approach to design an order entry system, for example. So that's that. And I have 5 minutes, is that right? Yes, okay, all right. So now I'll go into the last part of my discussion, which is just a couple like code samples to show it to you, comparing like RxJava and Pivotal Reactor, and also the Vertex and also Akka Streams. So first we'll just talk RxJava. So RxJava it came out of Reactive Extension. So Rx, it's actually, if you go to reactivex.io, you can check more things behind the scenes. That actually came out, this whole Reactive Extension came out of Microsoft. It's actually Rx.net came out first. And then they found it to be very useful, the reactive Rx aspect of it. So they essentially used the equivalent API, they ported it to Java. So that's Netflix, to Netflix kind of credit too. They did a lot of work with that. And that was back in 2014. But that was when the first time they came out, the version 1 was actually before Reactive Streams. So you may find that, yeah, they are using observable, and that doesn't actually have back pressure support in RxJava 1. But now too, with the reactive extension being so popular, then it's also been ported to JavaScript and the other language libraries, frameworks. For example, like Scala Closure also has Rx interface to it too. And RxJava in particular is very popular in being used in Android application too. So if I'm sure some of you maybe have worked with it as well. And then in 2016, that's when RxJava 2 got released, and that one actually has flowable, and that has also back pressure support as well. So just a simple HelloWorld to show it to you too, like using like RxJava 2. So you can tell too, like just HelloWorld like this, even though it's not like in reality we won't do it, but it's just illustrate to you is that it's a lot simpler in the programming syntax aspect. All you can do is you chain all these kind of commands together, and you just have one statement. You can do your hello world. So in this case, say using a flowable, you do a dot from array, pass in your arguments, and then you actually basically do a subscribe right there. So the subscribe will essentially print your result to the system console. So in this case, you run this, and hello somebody, whoever gets passed in will be shown. So you can see too, it's actually using, RxJava, it can be quite concise too in this case. So. And this is just an example of RxJava 2. In this case, it's showing you to how do you attach your producer to the consumer. So your producer in this case will be the observable. So you basically assign .just is the input stream, like how to do in Java, for example, like 5 strings. And then the consumer in this case would just output and have a system.out.print line, print it to the console. And then all you need to do is just attach your producer to the consumer by doing an observable.subscribe and pass in the consumer. Okay, so now we can then move on to talking about Spring Reactor. Actually, the Spring Reactor came from Pivotal, and it's actually very similar to RxJava 2 because the two engineering teams, they actually interchangeable, I guess, and they're members that work on both libraries. So you find them, for example, David Cannock, who's one of the leads on that project, RxJava, also contribute to Project Reactor as well. And Spring Reactor came out since Java 8, so it kind of, the interface is a lot cleaner because Java 8 has the streams and has Lambda functional programming support, so it makes full use of it. And just want to point out too, for Reactor, when you code it, you want to use the Reactor core library. And then there are other libraries, for example, for doing testing or integration with Kafka, RabbitMQ. It also has incubating reactive streams, also for .NET and JavaScript as well. And here is just an example too of using, comparing a traditional style of Spring MVC to kind of make a call to get some products. And then using the newer Spring Web Reactive Web Flux, the reactive reactor way of doing things. So just want to quickly show you too. So traditional approach, you use Spring MVC. You do if you run this, you see traditional way started. And then you go and make a call to get products. And in this case too, what will happen is that in the runtime, then this call will actually be a synchronous call, so it will be blocking. So this method will essentially be blocking and just waiting for the results to come back before it can proceed. So once the list of products come back in here, then you then see the next statement, which is like here, print out that print line that says traditional way completed, and then the list of products will be returned. Then your method will return in this case. However, using a reactive approach like Spring Web Reactive Web Flux, you see that over here, just basically do a get all, and it returns Flux. So Flux and monos are basically reactor way of managing the streams. And Flux is basically you can like return from 0 to like many streams, and mono deals with only 0 to 1 item, I suppose, yeah, that comes back as a stream. But in this case too, we're doing, you know, the two sets of code looks alike, but actually they function differently because the web flux way is an asynchronous way, a non-blocking way. So over here, when you run it, you first see reactive way using flux started, and then you make a call to do get product stream, which returns. In case two, what will happen is that before you actually get back your list of products, we will actually see like reactive way using flux completed, and then your method will return. And then in the meantime, it's actually the processing is being processed, and depending on how many records you're waiting for too, right? So in this case too, you basically, it will function the same way as like a sync, you know, the asynchronous style of programming. Basically, you make a request, and basically the results will go back to a sync. So when the sync is complete, then basically then you can do a regular HTTP, for example, your client to go get the results back. Or in this case too, it's just a quick example to point out, you can also make it a bit more truly reactive, or is basically you can have this client also subscribe to an event. And this is text event stream value essentially is kind of indicating that, you know, the client indicating that, oh, I'm interested in the server send event. So when the server is ready with the set of return that, you know, list of products, then you actually get notified of it too. But that I won't go into all the details, but I just wanted to point that out to you. Okay, let's see. I think I probably talked for too long. And so here is just a comparison between RxJava and Spring Reactor. I think most of the stuff I already point out, so I'll share the slides if you're interested. But they essentially are quite similar, the two libraries, because they are developed, especially RxJava 2 and Spring Reactor are developed by essentially the same group of engineers between the two. But want to point out that Spring Reactor is a bit more cleaner because it gets started at Java 8, and so it makes use of the Java 8 streams and functional programming. Okay, and then I will talk about Akka. So Akka comes out from Lightband, and IBM has a partnership since June of 2017. And it makes use of Akka Model, which I talked about earlier. Akka Model came out of Erlang in the 1980s. And it's a hierarchy, like a root hierarchy. So every system, you have actor, you always have a root actor. And think of it more like a parent and child type of relationship in your like hierarchy of all the components. So Akka is event-driven, and it has also very strong like location transparency and very lightweight. And it has this also as a special kind of feature to it is basically a supervisor capability. Supervisor, actually that concept comes out of the Erlang kind of concept too. It's essentially too, it helps with like recoverability and resiliency. Because if there are any error that occurs or any kind of situation, maybe back pressure too, is that your children, like actors, because in writing Akka code, everything is handled by actor. So even the children, you have actor. So let's say, you know, your worker node and children is handling something, some request, and it cannot, you know, take the load anymore. Basically, it can turn around and tell your parent actor and says, well, I'm under heavy load. Do something about it. So it has this hierarchy that enables itself to recover and bounce back and load balance very well. So yeah, if you're ever interested too, I have another talk actually I did in using Akka cluster too and on Kubernetes, but that's another talk. So, but I won't go into detail with that. But in here, I just do a quick thing to show you how do you do it in like a HelloWorld using Akka model. So here too, in main, you basically start up your akka.main, and here you start up your Akka engine essentially. And then HelloWorld, you remember everything is an actor. So you start off your HelloWorld class, and that's an actor. Think of it more like a container. And then over here, if you take a look into your HelloWorld, it extends abstract actor, and then the thing of interest is here, is the pre-start. So when you start off your HelloWorld, then it basically in here, if you see that it's actually trying to also start up another child actor. The child actor is actually the greeter class in this case. So all the greeter will do at this point, it will get instantiated, and basically then the greeter will basically tell, itself, like basically recognizing it is a greeting message that comes in, and it will print itself out. But we'll take a quick look into the greeter. The greeter itself also is an actor, so it extends abstract actor. There's also an abstract logging actor that adds in the logging capability too. But here, an example is just the abstract actor. What it does is, once it gets started up, it's essentially just waiting for events to happen. So once it has an event, then this particular call will be called, basically create receive. It's essentially when I receive, some events come in, message comes in, then I'll react to it. And it's basically then do this style of programming is doing, functional style of doing a match equals. If it's a greet, this is what I need to do, greet, then I'll just print out hello world, and basically then also tell whoever calls me, right, then says I'm done. And my other component that comes in, the requester, that says I'm done, and then it returns. So as you can see, using Akka, you're basically making use of like actors to handle all of your processing. But this is just a simple kind of example to show that to you. And here is an example in Akka in Scala too. And in Scala, by nature, if you're familiar with it, that's all functional style of programming. So this is how it looks like if you do it in Scala. You can tell it's actually cleaner than doing it in Java. It's just fewer lines of code. So again, I won't go into detail here, but just want to show you. And now the last thing to show you is basically Vertex. So Vertex comes from, is open source. Again, all these libraries I'm showcasing here Vertex came from Eclipse Foundation, and it's a very flexible, like polyglot framework. And it interoperates real well. That's its strength. It interoperates well with other frameworks. So like say in a Vertex application, you can actually mingle it in with like Ruby, for example, and JavaScript too. It's quite easily. That's the nature of it. And it doesn't make use of an actor model, but it's similar to it. It's called verticals. The verticals are basically being deployed and executed by the Vertex engine. Vertex itself is highly event-driven, and they run only when they receive a message. So it's kind of like Actor too, kind of you execute things only when you receive a message. And it has an event bus that handles all your events, and it's not restrictively tied to any container, and it can be used with other libraries too. And here's an example of HelloWorld, and we do an HelloWorld embedded in here. And so basically in your main, again, it can be done in one line. You can do a vertex.vertex and then do a .create HTTP server. And you immediately then you chain it and do a request handler, and then you pass in your request handler, and you have your request.response.end. And basically if it receives the message, then it will print out hello world in this case. And basically, when you start to the create HTTP server, you can do a .listen, basically binds your listener to, in this case, 8080 in this case. So you can see too, it can be done quite in this very simple kind of way as compared with traditional style. So with this is almost coming to an end, but just what I'd like to do a quick kind of takeaways. Some of the things I already talked about, but just want to point out ultimately too, for reactive systems, I've heard many arguments too that people are saying that, well, why we need reactive, but there's a reason for it, because it handles like concurrency very well too, and also other reasons too. The streams, for example, back pressure, things of that nature, asynchronous style on non-blocking calls. But ultimately too, what we're going after is really the responsive, very responsive applications, and that's kind of handle the failures real well. But one thing, all these I think I already talked about, but I'll just skip to the end, is basically reactivity is really not fully realized, because if you think about a relational database itself, it's still using like blocking I/O to handle, so like the relational database engine level. So that's not really fully all reactive, although right now there are efforts, and there are also database connectivity libraries. For example, like R2DBC comes from Pivotal. They are actually non-blocking I/O to handle database connectivity. reactivity. But once you connect to the database on the database level, that's still handling things in a very blocking fashion. So I just want to point that out. Okay, so with that, it comes to an end, and thank you for your patience with me. I probably talked more than I should have, but thank you for your patience. And if you have any questions, then please let me know, and I always welcome suggestions and your feedback too. And I also plan to we'll be starting a podcast too, to talk about. Then I'll be inviting experts like Olak and some of the pivotal folks and Josh Long and everybody, all of these reactive experts. I'll be interviewing them to ask more questions on this subject. And yeah, so please watch for me if you want to follow me on Twitter. And also too here, I'd like to invite you to sign up for the IBM Cloud. This is just a tiny URL, and IBM Cloud is free to all too. There's a free tier access, so anybody can sign up for it and try out the different things. There are also some Watson library, the AI machine learning libraries, IoT, yeah, you name it, everything IBM has it, somehow has it underneath the hood. So please, yeah, feel free to kind of sign up. And then these are the various links to get to some of the reactive resources. And also I'd like to invite you to sign up for IBM Java newsletter too. So here's the link to it. If you go to developer.ibm.com essentially, and if you go to just /newsletter, there are also newsletters for other areas like IoT, Watson, and open source, for example, things of that nature. So, and I think then with that comes to an end. I think, yeah, that's all I have. So again, thank you so much for your patience with me, and I appreciate it.